In the last video, I already talked about the base quantity. Now it's the time we go for the derived quantity. So first thing, the derived quantity are the quantity they are able to define in terms of a base quantity. And the unit is what we call the derived unit. And this can be formed by the multiplication of a division of this base quantity. Now remember that the base quantity is the things like a length and a time. So again, I will use the example, the speed is equals to x over t. And in this case, we know this x is a distance which have a unit of a meter, and this t, let's say, is a time, and it has this unit of this second, right? Now you can see in this case this is formed by the division because the x divided by this t, and they form the unit of the meter per second, and this is formed by the two base quantity. Let's take a look at another example. Let's say this ek. This is kinetic energy. This is equals to 1 over 2 mv square. Now this m is a mass. Mass have a SI units of a kg, and this v have a unit of a meter per second. Now since here is a square here, you can see the unit will become a kg meter square, and this per second square. Now by convention, we would call this a joule. This is a unit, SI unit for this energy. Now here is some example. You can take a look. This speed we already discussed, which have this unit, and acceleration is defined by the change in the velocity over the time. Now the velocity is not the same as a speed, but they have a same dimension and the same unit. But in terms of physics, concept is a bit different. We will come in to explain this later. So from here, we know this is a change in the velocity. Let's say this is acceleration. We write down is a, and the change is in the velocity is a delta v over t. So acceleration equals to delta v over t. Now delta v is have a unit of meter per second, and this t, you can see this is a divide, so divide by the unit of the time, second, and this is just equals to meter per second. This is equals to meter per second square, right? So we get this unit, and density usually is right as a rho using a symbol of the rho equals to mass over volume. And in terms of the unit, we know mass is a kg and volume is a meter cube. Again, this is a divide, so we can write now this is a kg per meter cube as here. And work done, this is a work actually, W equals to the force multiplied with this. Actually, this is a dot product, the displacement, so F dot x. Right. Now, force here, we know F is equals to ma, and here we already know the unit of this, the acceleration, and we know the unit of this mass is a kg, and multiply with this unit of the acceleration. So we have a kg meter per second square. And now we know this x is a displacement. Displacement have a unit of the meter. So this thing multiplied together, we get the unit of this work is given by ng meter square m per second square. Now notice here, this actually is the same units as a joule, as we discussed in the last page. We will go more detail on the physical meaning of this work and the energy in the later chapter. So for now, this is some example for the derived quantity. Now here come a concept. It is called the dimension analysis. This is a analysis method. We can check the homogeneous of an equation, which the dimension or this unit on each side of the equation should be the same. This, although this homogeneous is a fancy word, it is just mean that we need to have both sides of this dimension to be the same. So this is also what I would call the first condition for the equation to be correct. If you want to use this equal sign, that means you must satisfy this equation in terms of a physics. This is a first condition to this thing to be correct. If you use this equal sign, uh, if you check out this thing is correct, I mean the unit from both sides is correct, it doesn't mean that the equation in terms of physics is definitely correct. But if you find out this both side of the unit or dimension is different, there is definitely be wrong. That means they definitely incorrect. So again, I will emphasize again, if this dimension analysis, we find out these two sides have a same unit or dimension, it does not confirm the equation is correct. It does not. This is just the first condition. From the previous slide, we know about this kinetic energy is equals to 1 over 2 mv squared, and the work is equals to F dot X. Now, the question for you is that possible this kinetic energy can write as equals to the work? So let's find out, is this thing, this equation are homogeneous? They have a dimension unit on both sides of this equation to be the same. So let's check. This kinetic energy is given by 1 over 2 mv squared, and work done is given by Fx. Now this 1 over 2 do not have physical units, so this is just nothing to be considered. And m have a unit of kg. In terms of dimension, this is capital M. But actually, I prefer only use either kg or this n. I mean, either use a dimension or the unit. Otherwise, for those are new to this thing, maybe easy to confuse. Actually, personally, I prefer using the SI unit. So I will show you both way. First, let's find out this unit. And we know is meter per second, and here I have a square. Now F is equals to the MA, and this M have a unit of a kg, and acceleration have a unit of the meter per second square. and x. So let's write down here kg meter second square, and x is a unit of a meter. So let's consider this part here first. You can see it will form kg meter square and per second square, right? Now let's see this side here. Again, we get the kg meter square per second square, right? You see this both side, left and right from this equation is the same. I mean, the dimension and this unit is the same. So we can conclude this equation here is homogeneous. Now, let's talk about the dimension. This mass have a dimension of this capital M, and this velocity have a dimension of length L, and per this second is the dimension of time T. Here, because this is per, so this is a power of a -1. And remember, here have a square, so we have to write down this capital L and T multiply with this 2 on this power term. Now, you do the same for this work here. You will get this is the M, and this is length, and time power of a -2, and multiply with this the displacement, which have the dimension of length, and you can see the result is just the same. You will get the homogeneous result, and this is the same dimension. So this is one of the example. Later we will look at the more example. I would like to talk more about the concept of this dimension analysis. Now, as I said before, if we have an equation, let's say A over B, right? And the first condition for this equation to be correct, is that we must be this homogeneous. That means both sides of this equation must have a same unit. So you can see the A must have a same unit as this B. This is very reasonable. For example, we know the only human are possible equals to the human, right? For example, if we have a human, so we can do the addition, one human plus one human, we get two human, right? Now, clearly this impossible this human is equals to a cat. This is just impossible. So this is not equal. Definitely the human is not equals to the cat, right? How about the case, let's say, before this, you can see here, this is why we have to make sure both sides of this equation to have a same unit or dimension, right? The concept behind is just that simple. I think everyone can accept it. So let's consider the second case. Now, let's say we want to do the addition of a human plus a cat, right? The question is this possible? how do we going to make this if this is possible? The answer is it can be done by this changing of a unit, right? For example, in this case, we have a unit using the human, right? And this cat is a unit of the cat. Now, in this case, clearly the human cannot directly add to a cat, but we can change the unit to be something like living things, right? We can still make this thing out two living things, right? So by this we apply the changing of this unit, and that means actually from here we also have to change this to the human and a cat to be the living things, right? So by this we can make sure the equation of both sides have a same unit, right? But after all, about the base unit, remember the base unit like a meter, a second, and kg. This correspond to the dimension of a length and time, and this kg. Kg is mass in terms of a dimension. So why I telling you this? This is usually what we can do. For example, we know the x is a distance. X is a distance. Now we cannot directly plus the velocity, right? But we can plus the velocity multiplied with this t. So these two have a same unit, right? You can see this velocity is a meter per second when it multiply with this t. So t have a unit of second. This thing will just get cancelled out. So we get the same unit as this x. This is what we doing of this change of the unit. You can see this is how we do in physics. But in terms of this base unit, let's consider the case, let's say kg plus this second. That means we're trying to plus this mass to the time. This is just impossible. This won't be any reasonable result.